Last class we proved that for every regular expression there exists an epsilon n of a, and hence the language represented by a regular expression is a regular language. And today we are going to prove that for every regular language there exists a regular expression. So we will see how we can obtain a regular expression for a regular language. According to the definition, a language is regular when there exists a finite state automaton, and here we assume that there exists an n of a when we say that a language is regular. So we need to get a regular expression for a regular language, and this is the subclaim that we stated. Any regular language can be represented by a regular expression. We will have a constructive proof called Klein's construction, where given an epsilon n of a, we can construct a regular expression R induced by a, Ra, such that the language of the constructed regular expression is same as the language of the given epsilon n of a, and that is what we are going to discuss in this lecture. We will see some examples first, and later we will try to discuss some notations and definitions, and then we can see how the construction algorithm works. Consider this simple n of a. You can see that the language is just set A, and the regular expression for this language is nothing but A. Another example, here you can see that the language is this set, C is accepted and AB is also accepted, and the regular expression is C plus AB, and which is actually the regular expression for the path without passing through the intermediate state P, which is C, plus the regular expression for the path passing through the intermediate state P, which is AB. And this is a generalizable observation. If you look at a more interesting example, here if you look at the language, AB is there, which is without passing through Q as an intermediate state. The only string that you can accept is AB. So AB is definitely there. And now suppose you also allow Q as an intermediate state, then you can state the language as AC followed by, that is you are in Q. Maybe you can come back to Q using this loop many number of times. So AC followed by this DC any number of times, followed by finally DB. That's the language. I hope you are getting me. And you can now write the regular expression as AB for this plus AC followed by DC 0 or more times followed by DB. So it's basically looking at an intermediate state. If you look at Q as an intermediate state, first you are considering without passing through Q, what can be there? It is only AB. Then passing through Q as an intermediate state, you are saying, okay, what is the string taking you to Q, which is AC, followed by which are the loops coming back to Q, which is DC star, followed by the path which takes you from Q to the final state, which is DB. And if you want to write this regular expression and this like this, you can write it as C, which is without passing through an intermediate vertex or without passing through P. Then passing through P is A is taking you to P and there is no loop coming back to P, so it is epsilon only, epsilon star in place of DC star here, followed by B. And here you can write it as A plus epsilon because there is no other path, so it is epsilon only. And now with that observations, let us proceed and see some notations and definitions. Consider this example N of A. We can have a notation representing a set of strings. Basically a set of strings is a language. L subscript QF, which is actually CB, meaning it is actually the strings for which there exists a path from Q to F. It is the set of all strings for which there exists a path from Q to F. In this particular case, it is CB. And no doubt the regular expression is CB for this path. And if you formally define it, given an N of A, LPQ is the set of all strings W in the language, in the alphabet set of the N of A, such that there exists a path from P to Q with the label as W, and that is what we show. So LQF means the set of all strings W for which there exists a path from Q to F for W. In this case, it is only CB. Then look at this example N of A. We are going to see another representation here. We know that from the previous slide, what is LSF1? It is only AB, and this is the regular expression. You can notate it as regular expression for this set. Similarly, if you look at LSF2, no doubt it is AC, and this is the notation. Now you can see that if you look at the language of this N of A, it is nothing but the set of all strings accepted by the final state F1 union the set of all strings accepted by the final state F2. So it is the union of these two sets. So the language of A is nothing but the union of these two sets, one for each final state. And regular expression is of course the sum of the regular expressions for this. If you recall the semantics of the regular expression, when plus is the operator, it is not difficult to see that as it is the required regular expression. In this case, AB plus AC. And formally, if you are given with an N of A, then the language is the union of each final state LSF. In this case, LSF1 and LSF2, you take the union, you will get the language. And what is the regular expression? It is the sum, the plus between these two regular expressions. In general, plus over all the final state, the regular expression for each final state. Now, we need to see one more notation before we look at the algorithm that we need today. So here you consider this N of A and look at this notation. What is this? Without this set P notation here, everything else is clear. This means which are the strings for which there exists a path from the state S to the state F, which passes through P as the intermediate state. So only P can be the intermediate state. So it is AB. Now suppose you allow both P and Q as intermediate state, then this is the set of all paths. AB is there and also the other path AC followed by DC number of times followed by DB. and this is the corresponding regular expression. And if you formally define, given an n of A, what is LPQX is the set of all strings W for which there exists a path from P to Q with the label as W, which passes through only states in the set X as intermediate states. So you are not allowed to go through a state which is not included in X. So that is this notation. I hope this is clear. Then let us proceed and look at the last notation and definition which we need for the algorithm. So look at this example, and we are going to use the previous notation to define the language of this n of A. We know that what is LSF1Q? That is a set of all strings for which there exists a path from S to F1 which can pass through any states in the n of A as intermediate state. So we are allowing all states if possible. We can verify that this is correct. Then this is the one that you get for F2, and the language is of course the union of these two, and the regular expression is this regular expression plus this one. And if you formally define, the language is this: for each final state LSF Q, and Q is the only additional thing that we are introducing here. When it is Q, you are getting the language, and the regular expression is here. And now we have enough notations and definitions with us for formulating an algorithm to generate an equivalent regular expression from an n of A. Now, you can see how one can inductively define a regular expression from an n of A. Before we formalize, let us look at an illustrative example. Here is an n of A, and how will you define the regular expression introduced by A? You can do it as follows. It is the regular expression representing the path without passing through an intermediate state, which is only C, plus the regular expression representing the paths which goes through only the state P as intermediate state, which is AB, plus the regular expression. Actually, we need the regular expression for all the paths passing through P and Q as intermediate state. It is like you are coming to Q, AC plus AC. Then you are in Q now. You come back to Q any number of times, that is DC star. Then finally from here you are in Q, you have to go back to D, F through DB. So this is the regular expression. Okay, basically this is what we need to do. We can see formally how we can write this as an algorithm. For that, we need to solve an inductive definition or inductive equation or recurrence relation. So we are looking at this kind of a situation where we are looking at the paths going from the start state to the final state, and there could be a number of intermediate states. Now here, when you want to solve a recurrence relation, you want to reduce the size of that recurrence relation in the RHS, and here an attempt that we are trying to make is, maybe you have a set X of states and R as intermediate states, all the states in X and also R, and now we are trying to get a recurrence relation in terms of only X as intermediate states. So we are taking out of state R from the set of all intermediate states, and the remaining set is called as X, and R is just taken out. Maybe R is also an intermediate state, we are just going to take it out. Now we can define this, that is the regular expression for the language of string, for which there exists a path from P to Q which can pass through any states in X or R as intermediate states, any state in X or R. And in the RHS, we need to have an equation which is not using R as an intermediate state. That is the goal, which you can define as, you consider all the paths which are going from P to Q by passing through X only, maybe without entering the state R. There could be such paths, okay, the regular expression for R, for such paths. Plus, now you consider passing through X as intermediate state, you are reaching into R first. How will you write it? P to R by passing through X as intermediate states. Okay, you are reaching into R. Now you consider from R you are coming back to R again by passing through only the states in X as intermediate states, and that is what you are doing here. R back to R through X only. Then finally from the state R to Q passing through only X as intermediate state. So this is how you can write this recurrence relation. Note that in the LHS you have all the states in X union the state R. So R or any states in X, and in the RHS you are getting rid of the state R from the intermediate state set. Okay, and if you apply the same technique in X, you can take one more state out, and if you continuously do it, you can solve this recurrence relation. And this is enough for writing an algorithm now, and which is what is called Klein's construction, because it is proposed by Klein. And the first step is begin with this regular expression from the starting state to the final state. For each final state, what is the regular expression? If you are passing through all the states as intermediate state, that is actually the language. If you recall the language that we defined 2 slides before, then you have to apply this equation to solve. And not that in this case, suppose there are 10 states here in the intermediate state, in the RHS only 9 states. Again, if you apply, you will get 8 states, and eventually you will get 0 states like this. Suppose the intermediate state set is empty, then what can be LPQ? The regular expression for LPQ, it can be the label of the edge A if P and Q are not the same state and there exists an edge for the symbol A going from P to Q. No intermediate state means from P to Q, the only possibility is an edge going from P to Q. If A is the label, then it is A. And if both P and Q are same, if you look at PP, then it should be A plus epsilon, assuming that A is a self loop, and if no self loop is there, you will get only epsilon. I hope you are getting me, and for the interest of time, let us proceed and see how we can apply Klein's construction in obtaining a regular expression for a given n of A. The application will make the procedure more clear. Suppose we are given with this n of A, maybe we can manually write the regular expression directly, but that may not be possible for a large n of A. So just apply the algorithm as if you are a computer executing the algorithm. Don't apply any thinking here, just apply the algorithm. As the algorithm demands, we need to apply this equation for solving the recurrence relation, and if you recall, this is what we have to compute. By permitting all the states are in as intermediate state, we need to find the regular expression for all the paths going from S to F, and that is what we need. And if you apply this formula, maybe you can write it as, you take F out, so you can represent this as S union F. If you recall that picture, now this is the case. Previously there was a number of states were there, in this particular case only 2. You took out F. Now actually in this set, even though I pictorially represented it like this, only one state is there. And if you apply this formula, you can easily observe that it is nothing but the regular expression for paths going from S to F passing through S only, and that is what I am writing here. Then S to F passing through S only, then F back to F passing through S only, then finally F to F passing through just set S only. You can easily verify that this is exactly what this equation is asking you to do. Now maybe we can solve this equation. Okay, here you have only one state. If you take out, you can write it like null set union set S, and the situation looks like this. Now in this set, no state is there, it is null set, and this is the situation in up. And if you apply the formula, it is the regular expression for the pass going from S to F passing through null set. Okay, then S to S passing through null set, then S back to S passing through null set star, followed by S to F passing through null set. So this is exactly what we need. Now just try to solve this equation. You can see that if you look at this, from S to F passing through no intermediate state is only A, because this edge A. That is what the algorithm says as, plus, and what is this, from S back to S, okay, it is A plus B plus epsilon. You can either process a simple A and stay back, B and stay back, or you can stay back without consuming an input symbol, that is it. Followed by star of this we have already obtained, just star of this, and followed by LSF, which we already found as A. So this is the formula, which you can rewrite as this, because A plus B plus epsilon, the whole star, is actually A plus B the whole star, because A plus B star represents all strings over the set AB. If you remember that semantics, this rewriting is okay. And for the same reason, because this is representing all strings, this is not explicitly required, so you can write it as this, because this whole string can be represented by A plus B star, because A plus B star represents any strings over AB. So that's it. Now we have found solution for this SFS, and now it remains us to find FFS. And if you apply this formula, you can take out S and you will get it as this. That is FF phi union S, and this is the picture if you want. So how will you write it? It is from F going to F on phi as intermediate state, plus F to S on phi, followed by S back to S on phi star, followed by S to F on phi, and which you can directly solve. F to F on F to F without passing through an intermediate state is epsilon, that is, this is epsilon, plus what is this saying? From the state F back to S, there is no such path, so it is not, it is phi. Phi is that regular expression. I hope you remember the semantics of the regular expression phi, which is null set, followed by SS, which we already found here, it is this, followed by SF, which also we found here, it is A. And if you solve it, you can get it as epsilon plus phi. Why? Because if you look at this concatenation, null set concatenated with a set of string is null set itself by definition, and so this is correct, and this is what we are getting. So for this equation we are solving it as epsilon. Now you just substitute in this equation, you will get it as this. So this is the value we found for this, plus the same formula here, followed by ff star, that is epsilon star, followed by the same ff, which is epsilon, and epsilon star is epsilon, and concatenation with epsilon is this itself. So you will get this as the final result. Okay, and with this we are finishing this exercise problem, and what we have discussed today is a completely algebraic way of obtaining regular expression for an n of a, which is just solving a recurrence relation, and we saw how we formulate this recurrence relation and how we can solve it. And with this we are finishing this lecture, and I am giving you a practice problem for you to try and understand how the Clean's construction can be used to generate a regular expression from an n of a, and you can of course apply this for a DFA as well. So today we have seen an algorithm for generating a regular expression from an arbitrary n of a, and thus we can conclude that an arbitrary regular language can be represented by a regular expression, and thus with the result that we proved in the previous lecture, we can conclude that the language represented, or the family of language represented by the class of regular expressions, is precisely the set of regular languages. And thus now we have many equivalent, pairwise equivalent formal representations for regular languages, and they are DFA, n of a, epsilon n of a, regular grammar, and regular expressions, and all these 5 representations are proved to be pairwise equivalent. Thank you.